I'm going to talk about our midterm number 2. I'm going to walk through all of the questions and answers, um, as well as describe how to read the question and exactly how to sort of follow along. I'm going to put timestamps in the comments at the bottom. If you want to skip to a specific question, you should be able to do so within YouTube. So let's go ahead and get started. So this was question number 1. So it had 4 parts. That were all dealing with the same sort of bit of code here. So the piece of code is a recursive method. We don't exactly know what it's counting, right? But it takes as input a string and an integer, and the integer represents a position in the string itself, right? So we can see that the base case is when the pointer goes outside of the length of the string, and in that case it returns 0. Otherwise it's returning, down here it's returning count plus some recursive call where it increments C. So then the first question, part A, asks us what's the order of the worst case running time for each instantiation of the method. So here the word instantiation is implying that we're looking at one recursive call, excluding the recursive call itself. So one instantiation includes all of this code, right? But not this guy. So if we look, we're either going to run this if statement and then return, or we're going to run an assignment, an if statement, another assignment, a couple more if statements with assignments in them, and then one more assignment. So then the question is any of that code non-constant? Right? Is anything happening in this little chunk of code that has a loop in it or makes some sort of call to another method that might not be constant time? And the answer is no, which means that the order of the worst case running time for each instantiation is constant. Or in this case, because we're dealing with worst case, we could write O of 1. Right? So the next question says, well, what's the best case? So going back to our code, does anything here change based on the input itself? I mean, it could change because it might run the base case. But in either case, it's all still constant, right? So again, the best case is also constant. But because we're dealing with best case, like we said in class, we couldn't write big O, right? Because big O deals only with worst case analysis. So then the next question says, you run the following piece of code, right? This one little method call here, where the input string is not sure what, because we're not sure what we're counting, and the value of C is 9. And it's asking, including the initial call, how many times does the method run? Well, the first thing we need to do is figure out how big this string is, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the array length is 13. And we know we're starting the initial call with C pointing to that character, right? So then, if we look, it's going to run is 9 less than 13? No. So it's going to go down here and it's going to make the recursive call. So it runs it for C equals 9, and then C equals 10, and then C equals 11, C equals 12, and then 12 is not greater than or equal to input length, right? Because remember we said the input length is 13. So it does make the recursive call on C equals 13. And once we get up here, is 13 greater than or equal to 13? It is. So it stops making the recursion, which means that our answer here should be 5, right? And they are exactly these: 9, 10, 11, 12, and 13. Right? So then, now we've done a little bit here, and the whole point was me trying to get you to start thinking about how to answer the final question. So the final question says, what's the worst case running time of this method for a string of length n? So now we're going from a specific string to an arbitrary string with our initial value of c. So we already know it's going to run c all the way through it's going to start with c equals 0. It's going to make this recursive call down here at c equals 1, and then c equals 2, all the way to c equals n. Right? So how many instantiations is that? Well, it's going to be n instantiations, right? Because it runs once for each position in the string, right? And then one final time. So it's really n plus 1. But in terms of big O, so the reason we wanted you to do it in big O is because we get rid of that plus 1 term. So the answer here is the total worst case running time of this method, assuming you're given a string of size n, and an initial value of c of 0, is big O of n. Right? Because it's going to make one recursion for every position in the string. And then the bonus question here is, what's the method counting? Well, so in order to get in here, right, in order for count to even be 1, well, this if statement says that the value of the character has to be greater than lowercase a and less than lowercase z. So this is lowercase case letters. And if you look here, we're going to set it back to 0 if it's B, C, D, F, G, H, J, K, L, M, N, P, Q, R, S, T, V, W, X, and Z. So what are the things that so these if statements actually say that it's a consonant, which means that it's counting if it's a lowercase letter that's not a consonant, which means that the answer here was lowercase vowels. And in this case, vowels includes Y. So that's question 1. You actually needed both of these statements, lowercase and vowel, to get both bonus points here. But the main part of the question is here. It's constant running time, best case and worst case for each instantiation, and it's going to run, n recursive calls. Each one of those is constant time, so it's big O of n. So let's move on to question 2. So question 2 says, as implemented in class, what is the order of the worst case running time for bubble sort? So, remember we talked about bubble sort being the sorting method that goes through and it makes n passes and it looks for pairs of elements that are out of order and it swaps them if they are. Right? So, right off the bat, if we're doing a sorting algorithm, can it run in time less than n? Right? Order n means you're looking at every element a constant number of times. Which means log n, you're basically saying there's some elements that you're not going to look at and you're just going to assume that they're sorted. So log n is out of the question. Could be n squared. Right? But you're thinking to yourself maybe, how did we implement it in class? I don't know. I don't remember. I don't have notes in front of me. Well, I kind of gave you a hint here, in that the way we implement it in class is exactly written down here for us. So if we look, this is iterative bubble sort, so non-recursive bubble sort. Takes as input a set of integers. It runs one for loop over the length of the array, and then runs a second for loop up to I. Within that, it has an if statement that does some stuff. So if we were going to analyze this, we would start at the inside and ask ourselves, how long does this if statement take to run? Is there any sort of looping in here? There's not. So this is constant time. And then how many times does this inner for loop run? Well, it runs I times. And this runs n times. Which means our total running time is 1. It's actually n plus n minus 1 plus n minus 2 plus 2 plus 1. Which it turns out is big O of n squared. So, as we implement it in class, before we make any changes down here, what's the order of the worst case running time of bubble sort? Well, it's quadratic. What's the best case running time of bubble sort as implemented in class? So looking down here, if the input is any different, does it change the loops that we go through? No, it doesn't influence the loops. So whether or not we run the body, it's still a constant amount of work, which means the worst case as implemented is also quadratic. So then that leads us to the final part of the question, which says, if we know the list is already sorted, right? If we know the list is already sorted, we don't need to do any extra work, right? We can just stop. We already know it's sorted. So we want to add lines to the code in the solution from class only in the blanks below. So there's 5 extra lines to use at specific locations. And we want to do that so that in the best case, so the best case here is when the list is already sorted, it takes only linear time to complete. So this is a learning experience here. So we're saying, this is the best we can ever hope for, since to ensure that a list is sorted, we have to examine every item. So let's think for a second how bubble sort works, right? So bubble sort, like we said, goes through and it looks at pairs of elements and checks to see if they're out of order. So if we assume, as we do here, that the list is already sorted, if the list is already sorted, are we ever going to find a pair that's not sorted? No. Otherwise, our original assumption would be false. So all we need to do is ensure that this inner piece of code here, if it's already sorted, this guy is never going to run. If it's not sorted, that will run at least once. So how do we write a piece of code that checks to make sure some other piece of code is never run? Well, we can use some sort of indicator, right? And when we think indicator, that word usually points us to a Boolean. So let's define a Boolean. Boolean is sorted. And before we get to what we initially set it to, how is it going to work? So we're going to have this Boolean, and it's going to be set to some value. And when it's set to that value, and it never runs this inside bit, right? If it never runs the for loop, then the value doesn't change, and we can do something down here to make sure we exit the loop. So do we want this to be positive or false to start with? Well, given the actual name of the variable, let's say that it's positive. So we'll start with it equal to true, which means that inside this for loop, or inside the if statement, if we ever come across a pair that's out of order and we need to swap them, then we need to set it equal to false. Okay, so now we have this Boolean that tells us if we get to this line, right, and we haven't made any swaps, is sorted is still going to be true. It means that we've checked every pair and all of them are in order. Therefore, the whole thing is in order. So in that case, what do we need to do? Well, we know we need to return down here somewhere. It's a void method, so we just use return with no element. But then what kind of control flow do we need to execute that? Because if we just leave it like that, it's always going to return. And it's only going to make one pass, which means our array is not necessarily sorted. So we need an if statement. So basically this says we start with this value. We're going to assume that the array is sorted until we see otherwise. Well, if we do see otherwise, that means that there's a pair of elements that are out of order. So we set this equal to false, which means we don't execute the return statement. If we don't see a pair that's out of order, that means we were actually all the way sorted, which means we're true when we get here, and it does execute the return. So in that case, if it ends up still being true, what's the running time? Well, it's going to make one pass here. It's going to make one pass of this, which is O of I, right? In this case, I on the first iteration is N. And then it's done, right? This is O of 1. And it exits. So the best case running time here, best, is linear. Right? Because it doesn't do any more of these guys. And then what's the worst case? Well, assuming this does get set to false, it's going to keep running, and it will run n of these, which means worst case is still n squared. Right? So that allows us, in the best case, to short circuit it. Okay, so moving on to question 3. Question 3 was another debugging question. This is similar to the one we had on midterm 1. So the following method is supposed to implement binary search on an array of strings, right? So again, we're assuming that this set of strings is sorted in some order, and we're looking for a particular string, and we're given a range, right? But we've implemented this implementation of binary search has some problems and a typo. So we're going to ignore that one, right? Because that's what I said to do during the exam. Ignore the missing semicolon. And we're still looking for other issues. So let's read through the code, and then we'll come back and try and find them. So as is with standard for binary search, the base case is when the end value is less than or equal to the start value, right? That means that we have some array and end comes before start, which means the range is negative. So that's okay. And then we set mid equals to start plus end over 2, which a couple people said that this was wrong because it should be start plus end minus start. over 2. But as we showed in class, these are actually equivalent, right? So this is actually 2 times start over 2 plus end minus start over 2, which means it can be 2 times start plus end minus start. And this cancel, right? Which gives us this guy. So that's not an error. Okay. Well, that's okay. So then we say if input mid is equal to search. So that seems right, doesn't it? Where you're asking if the midpoint is equal to the search value. But the key here is to remember that we're dealing with strings. So, can we use equals equals on strings? We can't. So, our first error is this guy. And why is it an error? Because equals equals can't be used with strings. How do we fix it? Well, we use dot compare or dot equals. Right? We could use dot compare to. In that case, compare to tells us whether the thing we're searching for comes before or after. It gives us a value either positive or negative. But if it's equal, that would mean dot compare to would be equal to 0. So we could have said, or dot compare to blah equals 0. Either of those was acceptable. Okay. So then, now we've found that. So that's wrong, but we fixed it. So then, if it is equal to the thing we're searching for, then we found it, and we return true. Otherwise, we didn't find it, and we return false. Well, if we always return false, does it ever execute the rest of the thing? It doesn't. So there's our second error. Right? It's this guy. So returns on first iteration. Remove else and contents. Well, let's check it out to make sure Dr. DeBlazia didn't make any more mistakes. Maybe we can get some bonus points. So, assuming we don't exit immediately, we're going to say if mid.compare to search is greater than 0, we're going to search the front half. So what does compare to do? Right? We talked about this in class when we were talking about strings. Well, it gives us a positive value if the thing, the subject, which is input.mid, or input mid, if that comes after the argument. So if this comes before that, the value is positive. Sorry, if this comes before that, the value is negative. Which means we need to start, so if it's positive, that means we need to search the left. If it's negative, we need to search the right. So this is actually correct. This is correct. We're giving it start mid minus 1, and we're giving it mid plus 1 and end. Notice that we've already checked mid, so we don't need to include it anywhere. And that's the only error. Or those are the only two errors. Right? So, once again, I said to everybody at the end of the last midterm, this problem, like this particular question, we've seen it before. Right? And I said it's going to be on every midterm until everybody gets it right. And guess what? Not everybody got it right. So guess what's going to be on the next midterm? This question, right? Keep an eye out for it. Should be easy points on the next midterm. So question 4 asked us to match the quadratic sorting method with its pictorial representation, right? Match the sorting method to the image at the right that explains it. So we've come back to these images multiple times, right? They're easy pictorial definitions of what each sorting method does. So which one of these is insertion sort? Well, insertion sort is this one. And the question is, why is it represented by this particular image? Well, it's because insertion sort takes leftmost unsorted item and inserts it into the correct position in the sorted part, right? So it's going to take this yellow one and it shoves it into the right location here, right? So that's why that's the picture for it. Okay, so question 2 is bubble sort. Which one of the remaining 2 is bubble sort? Well, it's the top one, right? We've already seen bubble sort on the midterm so far. And basically what it does is it makes a bunch of passes and it swaps things that are out of order. So bubble sort makes multiple passes and swaps neighbors that are out of order. Right? This is what this picture is telling us. It's looking at neighbors and it's swapping them. Right? So then finally, by power of deduction, we know that this guy is selection sort. So why? Why does that one represent selection sort? Well, selection sort finds the item to go in the next unsorted position. Yellow. Finds the next item, red. Right? So it goes out and it searches the unsorted portion to find the item that should go there, and then it swaps them. Right? So I think most people got a good chunk of the points on this question. So I'm not going to go into many more details. But it seems like we all sort of know what these pictures mean at this point. Okay. So then, question 5. Question 5 was the one that a lot of people struggled with. And I think this was mostly mechanics, and possibly some not quite reading the question all the way. So, when I give you a lot of details on a question, it normally means that I'm asking for something very specific, right? So you should read all of those details and make sure you understand them. So, we'll read it together. We know merge sort is a recursive method that splits an array into smaller pieces. So I basically just give you and sends them off to be sorted, then merges the results. So that in and of itself is the sort of one sentence summary of what merge sort does. That's the pseudo code right there. Merge sort splits an array into smaller pieces, sends them off to be sorted, right? This is the recursive calls. and then merges the results. So assume that our merge sort method has the following signature. So this is telling you that we're using merge sort where it copies arrays, right? We saw there's a different version in the book than the one we saw in class, but the one we saw in class takes an array, makes copies of the smaller parts, and sends them off to be sorted. Note that the input is only an array with no indices, right? So this is basically saying this is not exactly the way it was done in the book, but it's the way we did it in class. Okay, so we've now defined the problem. And the question is, given the following input array, so we're given this array 4, 1, 7, 0, negative 1. Use the table below to identify each recursive call's input. So this is the left column. The parameters, basically the input subarrays to the recursive calls. These are the middle two columns. And the state of the array after the merge step. So that's basically just the sorted input. And then we go on to specify that the larger half, which it's not really a half if it's larger, but the larger of the two splits goes to the right. Right? So I made a point to tell you it goes to the right. And then if one of the recursive calls doesn't make any more recursive calls, right? So if it's the base case, we're going to put an X in the middle two columns. And then I gave you a hint. I said each non-X cell in these middle two columns becomes a row in the table. And then I started off by giving you an example. I said, if the input array is the whole thing, 4, 1, 7, 0, negative 1, the input array after the merge is the sorted version, right? You can see negative 1, 0, 1, 4, 7. That's just the sorted version of the same thing. And we know merge sort, as we said earlier, merge sort takes an array and it splits the array into smaller pieces. It doesn't change the order, right? It just splits the array. So in this case, we're going to split it into a piece that's 2 and a piece that's 3, right? Because we have 5 elements. And it said here, larger halves should go to the right. So that means the set of 3 is going to go to the right, the set of 2 is going to go to the left. So the input to our left recursive call is 4, 1. And to our right recursive call is 7, 0, negative 1. And then using that hint, right, each non-X cell in the middle will correspond to a row. So that means this guy goes here, right? This is one row, 4, 4, 1. And then this guy goes here, 7, 0, negative 1. So then we can actually fill in the last column pretty easily. No matter what we do for 4, 1, what's it going to look like afterwards? Well, it's going to be the sorted version, right? So 1, 4. The question is, how does it do it? Well, it splits it in half. So each side is going to be one size. It's going to be size 1. So then the left column is 4. The right column is 1. And again, each one of these becomes a row. So 4, 1. So then we work on the next row, 7, 0, negative 1. Well, it said that the bigger half goes to the left, or to the right. So we're going to have that split. So then we have 7 going to the left, and 0, negative 1 going to the right. What's it look like afterwards? Well, it's going to be negative 1, 0, 7. So then we're going to copy these down, 7, 0, negative 1. We'll work on those in a second, right? But we don't want to forget about them. So then, what about a one-element array? Is a one-element array ever unsorted? No. That's our base case, right? So it doesn't make any recursive calls. Same thing here. Same thing here. So then, is the input any different after the merge? It's not. So, same thing here. 4, 1, 7. Okay, so then this next row, 0, 1. Well, it gets split, right? 0 goes one side, -1 goes on the other. And then after we do the merge, it's going to be -1, 0. But we need to copy these down. 0, -1. And they don't make any recursive calls because they're one element arrays. 0, -1. So that's all I was asking in this question was, I want you to tell me what it's doing. So some people might have only ever seen merge sort as a tree, right? So you could draw all the same things on a tree. We have 4, 1, 7, 0, 1. Sorry, -1. And we could say the pass back is -1, 0, 1, 4, 7. Should have done that in a different color. And then that makes a recursive call to 4, 1, which turns into 1, 4, and to 7, 0, -1, which returns -1, 0, 7. Right, but all of this information is exactly the same. It's just written in a way that's easier to grade, right? So if you had drawn this tree and then copied the information in, that would have been fine. But that's all I was asking, right? Was give me the recursive calls. I don't even care how to implement merge sort, right? We never actually talked about the implementation other than the input is only an array. So this is the solution to this problem. Moving on to question 6. So in question 6, we're assuming we have the following method. It's a public static integer method called changes. It takes as input a character array and an integer x. The method itself, if the input length is less than or equal to 1, it returns -1. Otherwise, input 0 turns into the character a. X gets incremented by 7, and we return 7. And then what we want to know is what's printed when we run the following code snippet. So we start with an array with an f in it. So this is a one-dimensional array with one item. We start with an integer a equals 0. And then we set b equal to the return value of calling changes on the array and 0. So what happens when we call this? So the key here was the topic we discussed at some point during class was that arrays in Java, when you pass them, you're not passing the value, you're actually passing sort of the array, which is shared both in this context and in this one. And I just pointed out that I have a missing semicolon again. So when we go in and change the value f to an a, it changes it both here and here. But integers, or primitives as we call them more formally, integers make a copy and send that. So when we increment x, we're only incrementing it in this context, not in this one. So that means that the print here is going to be the array value at index 0 is. So again, because arrays are non-primitives, it's updating both copies. So that changes your f to an a, right? But because integers are primitives, the next line, the value of A is, well, the value of A is still 0. Right? Because again, A is a primitive. It's an int, not an array. But then what's returned, B, is 0 plus 7. So the value of B is 7. Right? So this question was asking all about passing primitives. Primitives versus non-primitives. And then for the extra credit question, you wrote a recursive question, a recursive method, but then executed it and it caused a stack overflow. What's the first thing you do? So there's multiple things you can try first. One of the main things is adding a print statement to make sure your base case is executing correctly and all the values are what you think they are. Examining your base case and making sure you have one. All of these were acceptable answers here.